So, tutorial 1.5 is on spaces on these region objects. The region objects in NGSolve are either subdomain regions or boundary regions. Both are region objects, and it's good to know about them, because you can do operations with regions that are often useful for complicated domains, and you can integrate on certain regions, and you can compress finite element spaces if some regions are not of interest, and so forth. So this tutorial is devoted to those topics. Okay, so now we, instead of the unit square, we have a rectangle. We're making progress. So, okay, it's a yeah, I'm sorry. It's this rectangle is a square, so don't get excited. You're right. Yeah. Okay. There is a real rectangle in there. So we're making an outer rectangle using the OCC, or Open Cascade, and we're marking. There's going to be a longer tutorial on OCC tomorrow.
Do as much as you want. I skip the parts.
Okay. Right. Okay. So. So you will see the syntax for OCC. There's documentation on that online also, and you can name the edges of a rectangle by pointing at, for example, like this. It says pick out the edge which has a maximum x value and call that right, or R. Pick out the edge which has a minimum x value, call that left. And similarly, bottom, top, and then draw another rectangle inside. And you do that by moving the point to wherever you want the other rectangle to start, and describing the dimensions of the rectangle. Okay. And here this rectangle is going to be submerged inside the outer rectangle. So there's going to be an interface inside the element, and that is inside the subdomain, inside the outer subdomain, and that's called interface. And if you want to think of the inner rectangle and what's left out by outside, well, then you have to subtract the inner domain. So the outer domain is now after the statement, the outer domain does not contain the inner rectangle. Okay, so picture does more than all the explanations that I just said. Here's the inner rectangle, and here's the outer rectangle. Okay. So that's how we make a very simple domain in using the Open Cascade geometry, and then we can mesh it. And you see the mesh respects the subdivision that we laid out. There's an inner rectangle and an outer rectangle, and they are different regions in the same domain. Or we like to think of it as subdomains. These are two subdomains, inner subdomain and outer subdomain. And if you ask for the type of this object, the subdomains, you can think of them as materials, or material subdomain. Then mesh.materials inner gives you an object that you see is a region object. And you can do this, a similar thing for the boundary. We mark the boundaries as bottom, right, top, and left. And if you look at mesh boundaries B, you see it's also a region object. So both boundaries, parts of the boundary, and in subdomains, they're all region objects. Okay, now here is an example of a finite element space defined only on a subdomain. Okay. We say that there should be a Lagrange finite element space defined only on the inner rectangle. Okay. And you can construct grid functions that belong to just that finite element space, so you don't have to, the values outside don't participate in any computation using this finite element space. Okay. The next point is about the number of degrees of freedom. If you have a finite element space that's on the whole mesh including the inner and the outer subdomains, and you have the finite element space that we built before, FES1, which is defined only on the inner, you would expect one to have significantly less degrees of freedom, but the end-of does not reflect that. Okay, so we need to know what is happening behind the scenes. It's the same business that we saw in the Dirichlet boundary condition implementation. You're constraining some nodes using the freed-offs. So if you print the freed-offs of the inner subdomain, you will see that a lot of the nodes, a lot of the entries in this bit array are 0. There's only 1, 2, 3, 4. I can't count it. Sorry. There's a handful. There's 2 handfuls of freed-offs, and everything else is unconstrained. Okay, and you can also understand the same information by printing out the coupling type. You see the wire basket degrees of freedom we saw before. You see something new called unused degrees of freedom, and you see, well, that's it, unused degrees of freedom. Unused degrees of freedom are the degrees of freedom that are falling outside the inner region. And it's possible to remove this degree. If you wanted to do some computation involving only this inner subdomain, it doesn't seem reasonable to store this lengthy vector of degrees of freedom, both the inner and the outer. So you can ask the finite element space to be compressed so that grid functions from that will only have degrees of freedom corresponding to the inner subdomain. And then you see the right number of end-offs after the compression. You can integrate on regions, and this is more or less as expected. What you need to know is this syntax. You can, when you integrate using dx, into dx you can pass an argument. You say that this volume integration should only be performed on a region. And how do you specify the region? You specify it using mesh.materials and give the region name. And similarly, you can ask for integration only on a part of the boundary, and like for example, only the top part of the boundary, and that's how you do it. So we've just made a source term that looks like a sum of 2 integrals, one using U1 and one using the top boundary. Okay, I should mention that if you look at the documentation of DX, you'll see this. Look for this optional union of string and a region object. This means, okay, where is it? You see it here, optional union. This means that you can, instead of giving this object, which is a region object, you can also just give it the string, and it knows to extract the region object from it. So you might, instead of writing this lengthy expression, you might as well have written this dx with a string inner. Okay, we can solve a problem, and then we can look at the problem, and you look at the solution, and you see, well, something happening in the inner region. Okay, operations with regions. So, given any mesh, you can ask for a list of all boundary regions. You can ask for a list of all subdomain regions. This is how you do it. Get boundaries. You see that there is four edges named interface, and another 4 edges named bottom, left, right, top, and so forth. And here's a list of all subdomains, inner and outer. We know this. That's how we made the domain. But in case you forget, you can always get this information, or if somebody gave you a mesh, you can query the mesh for this type of information. Okay, those of you who like regular expressions are going to like this. You can play all sorts of games with regular expressions using the names. So you see here, the first one is you're creating a mask. A mask is a bit array of which extracts out materials inner. You can do fancy things. You can extract all material. This is saying extract all materials using a regular expression, or you could say extract things in the top boundary and the left boundary. The vertical bar is OR in regular expressions, and it's useful because you can now do things like this. You take it, the inner material and outer material, and maybe if you have like 10 different materials and you want to do operations on different materials, and you can go crazy with this masking. You can take the complement using this little tilde. If you overlook that, the tilde is the complement of this, like taking the complement of a set. You can take the complement of a region. You can subtract regions. Here's one region, the total inner and outer, subtract the outer region, and then you can ask for the mask to verify that it did the right thing. And more interestingly, for finite element computations, you can set piecewise constant coefficient functions. So a material CF allows you to prescribe a domain-wise coefficient function. You say that the coefficient function in the inner domain should have this value, and the outer domain should have this value, and then you pass this dictionary into the material CF, and it makes a piecewise constant function with the values you gave, 3.7 inside and the value 1 outside. You can also do the same with boundary regions. For example, here is a dictionary of boundary values. On the bottom boundary, you want the value x, you want the function x. On the right boundary, you want the function 2 minus y, and you want to stitch them up together to a boundary coefficient function, and you put boundary coefficient and boundary you pass the dictionary as an argument to it. Okay, and now if we can't plot it like this, because how do you plot a boundary coefficient function? So one way to see if you've done the right thing is to interpolate that function using the set only on the boundary, and then look at the interpolated function, and now you'll see that the interpolated function has the boundary values you set, and it's cut down to 0 as expected when you do set on the boundary. Okay, questions?
What's going on with mask? I'm a little confused at what it's really, why is it printing those numbers?
Okay, let's see. So this is, for example, here. This is a bit array, and it's telling us among all the boundary regions which ones are to be selected. So here we said T or L, right? And the number, there were 4 interface boundaries in this domain, and T, L, B, R. Right. So it's selecting just T and L, and you know the position or the order of of the boundary segment by looking at the mask.
I see an inner is 1, 0, not outer with 0. Okay.
It corresponds to mesh.get boundaries. So if you print mesh.get boundaries, you see the list, and this is are the indices in the list.
Yeah.
And so this could be used for, this probably wouldn't go into bilinear forms particularly, right?
It's more about when you do region operations and making sure you're prescribing the region operation in the right places. And okay. So here, what Christopher was saying, so in the interface, in the first 4, you don't select the first 4, you don't select B, you select L,
right,
and then you don't select R, and then you select T.
And this feeds into other things. I guess I'm asking what other things it feeds into.
These are convenience facilities. Okay. Like for when we did the boundary coefficient function, where was it? Material. When we did the boundary coefficient functions, we said define it on B and R, and you could do. These are things when you make up coefficient functions, you want to know that you're setting it on the right place.
So you don't ask there.
You can also, for example, where it's very convenient, you can ask some domain for its boundaries, and then cut that with some other boundaries, and then define an integrator only on that part.
Oh, complicated. Okay.
So that you would use the mask and feed it into something else then?
Into the integrator, into the linear form integrator, for example.
And it uses those bit arrays.
I think you can try this. So get extracts inner region. We can use cell.
Yeah. What do you want me to do?
Dot
materials inner.
Inner. Dot
boundaries.
Dot mask. mask. If you type dot mask now, then you see the print.
Printed, yeah. Where would you use that?
And now you say materials inner dot boundaries or get boundary.
Dot boundaries.
Ah, okay. You can get band. Okay.
Just insert the boundaries. Yeah. Boundaries.
Sorry.
Yeah.
Dot mask.
Princess.
You want the mask?
Yeah.
It should have.
Ah, okay.
This is
Yeah.
boundaries of the inner.
Okay, interesting. I guess I'm asking because you have the free DOFs and that's a bit array and you use that all the time. I'm wondering where you're saying in an integrator you would need the bit array.
Also, if you want to evaluate, like for example, a function over some interface, you want to integrate it, or you want to compute the average on that. You want.
Yeah. Cool.
Yes.
This
Peter.
has a small bit arrays relative geometry. The trade-offs are huge. There's a million triangle instances are allowed bit arrays.
Peter.
If you wanted to make a finite open space on the boundaries, so you have to find on mesh of boundary B or R there.
Yeah.
You can just say H1, well, or not H1. You can H1 and then just define mesh of boundaries, and it'll produce. It doesn't do two H1s with a discontinuity. It actually connects them together.
I don't know.
Did you see what I mean?
Yes. Okay.
That's a surface file? Yes.
Yeah.
What you can do.
So you're saying H1 mesh, but defined on
Equals
mesh.
the B or R. That's going to be
It's going to be an H1 finite element space on the union of these two boundaries. Oh,
Yes.
okay.
And now create a grid function on it and set the vector to 1, and you see where it is defined.
Can you see something? Yeah.
I'm hopefully sure.
Okay. One, do you need the BND or no?
No. With BND. Either you say you define on, but I would.
Oh,
You can also just set the vector to 1, for example.
okay. We can do that. Okay, and then draw.
Yeah.
Are you sure I'm not going to crash?
I may withdraw, I'm not sure. No.
Oh, okay.
You have to evaluate it then at the boundary, for example, because it cannot draw volume.
Right. Yeah.
If
So
you make a 3D mesh, then you can easily do it. The mesh is Unicube generate mesh. Dot generate mesh.
okay.
You have 2 H.
Mesh equals
Oh, sorry. I'll fix that.
mesh.
Does Unicube also has BR boundaries? Or?
And then you have
What is-
top, for example.
Okay. Okay, and
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 not
then
draw
draw
the
G.
sorry.
And then draw this G.
Okay, let's see. Top. Okay, there we go. I guess we're facing top. Yeah.
Wow.
Okay.
And then you can compress. You can compress that.
Yeah.
That's a good place to compress.
Yeah, there's a lot of things to compress here.
Take this of ends off. Now 1200.
1200. Okay. You want me to compress and compare?
Yeah.
Compress. 144. Okay, that's good compression.
Perhaps this is also a good time to discuss why you had the mesh around the object that was generated. Go up.
Oh.
Where? Sorry.
Go up a bit.
Yeah.
NG mesh.
Yeah, down. This is cell.
Oh.
You have the mesh around the generated mesh.
The one you just
We
were
can
in.
discuss.
Ah,
There's
yes.
2 types of meshes, right?
Ah.
We discussed this yet.
Yeah, we haven't. Yeah. So this thing is a netgen mesh, which is interesting. But mostly we work with the NGSolve meshes, and so doing the mesh of a netgen mesh makes a netgen mesh into an NGSolve mesh. And if there are further secrets, please tell us. I don't want to go into the one-based, zero-based, and no.
If you can say netgen mesh, it's just meshing, and for finite elements you need a lot more information that is computed on the fly
Right.
than just automation.
Yeah. Okay. Yeah.
With
Peter.
that unit cube one, could you just give it the boundary to H1, or do you have to give it mesh defined on? Like.
Oh, you could have just done. I think you could have.
This is a region.
No.
Oh, you can't.
Then it thinks you want to define it on a on a
On the volume.
No.
So if you give a string, it will define
Yeah,
the
that's
volume.
true. Yeah. Okay.
So what was that?
There. No is the answer.
Yes, but it does something different.
Okay. Now I think it's a good time for coffee. Question.
I see the onto the subdomain is one solution to the white, the red and the blue colors. There's no any transition color like the yellow or green color on that.
Yeah.
If you go up like 22, well,
Yeah, discontinuous functions.
oh, that is continue function.
No, you can't just
This one. This.
I'm sorry, yeah, move up the number 22.
Oh. This one.
Show the graph to the information for this one.
Wait, 22. Sorry, 22 or 21? This one? This one? This one, yeah.
Rotate, open controls, object, close the objects, deformation slider. Now you see there is a discontinuous function.
It's a constant function on the inner subdomain and 0 everywhere else.
What happens on the unit cube when you do that?